All right, let's jump right in. We're going to take a classic algebra problem, something you've probably seen before, and look at it from a completely new and honestly much more powerful angle. Get ready. So let's start with a bit of a puzzle. Take a look at this equation. You see the x squared, you see the y squared, and you're probably thinking, okay, I know this. But then, bam, there's this minus xy term smack in the middle. What is that doing there? That one little term complicates everything. So what are we looking at? A circle? An ellipse? Let's figure it out. Before we can even think about tackling that messy equation, let's take a quick step back. We need to revisit the world where these shapes live. You know, the neat and tidy world where everything lines up perfectly with the x and y axes. Yeah, when these shapes are sitting pretty, perfectly aligned with the axes, their equations are super predictable. It's like a cheat sheet, right? A parabola only has one squared term. For a circle, the x squared and y squared have the exact same number in front. For an ellipse, they have the same sign. And for a hyperbola, they have opposite signs. It's all so clean, so organized, all based on those squared terms. Okay, so what throws a wrench in this whole beautiful, orderly system? What takes our perfect shapes and just knocks them sideways? Well, let's meet the villain of our story. This right here, this is the general form. It can describe any conic section you can think of. And look, right there in the middle, you see it, don't you? That bxy term, that's the guy we never see in the easy textbook examples. And here's the big reveal, the key to this whole thing. If that b coefficient is anything other than 0, that xy term shows up. And its presence is basically a giant flashing neon sign that says rotated. It means our shape isn't sitting straight anymore, its axes are tilted. So, how in the world do we deal with that? I mean, we could try to wrestle with the algebra to twist the shape back to normal, but that sounds like a nightmare. But what if there's a smarter way? What if, instead of moving the shape, we just moved ourselves? I love this analogy. It's perfect. It's like a picture hanging crooked on the wall. You don't usually take it down and rehang it, you just tilt your head. The picture doesn't change, just the way you're looking at it. And that's exactly what we're going to do mathematically. We're going to create a whole new coordinate system that's tilted right along with the shape. We'll call this new perspective our x prime, y prime system. It's really just the original x and y axes, but we've rotated them by some angle. We'll call it theta. And from this new tilted viewpoint, all of a sudden that crooked, complicated shape is going to look perfectly straight and simple again. Okay, so that's the big idea. But how do we actually do it? Let's get into the nitty-gritty, the actual formulas that make this magic happen. These two formulas right here, these are our secret weapons. They're like a universal translator, a bridge that connects the old straight world of x and y with our new tilted world of x prime and y prime. The game plan is actually pretty straightforward, even if the algebra looks a little hairy. Step 1, take our original messy equation. Step 2, everywhere you see an x or a y, you substitute in those big chunky rotation formulas. Step 3, brace yourself and simplify all that algebra. And if you do it all correctly, something really cool happens. Poof, that xy term, the one that caused all the trouble, it completely disappears. It cancels itself out and vanishes into thin air. And what are we left with? A beautiful, clean, simple equation in our new x prime, y prime world. Just look at this example here. That after equation, we know exactly what that is. It's an ellipse. Problem solved, just by changing our point of view. Now that whole process is super powerful. But let's be honest, it's a lot of algebra. What if you're in a hurry? What if you don't care about graphing the thing? You just need to know what it is. Is it an ellipse? A hyperbola? Come on, there's got to be a shortcut, right? Well, you're in luck. The answer is a big, emphatic yes. In fact, it's one of the coolest, most elegant shortcuts in all of algebra. A way to identify the shape instantly with just one little calculation. It's called the discriminant. All you do is grab the numbers a, b, and c from that general equation, and you plug them into this simple formula, b squared minus 4ac. And here is the truly beautiful part. That number, whatever it is invariant. That's a fancy word that means it never changes, no matter how you spin or rotate the shape. It's like the shape's DNA, its unique fingerprint. So here's the bottom line. This is the ultimate cheat code. You calculate b squared minus 4ac. If the answer is negative, bam, it's an ellipse. If it's 0, it's a parabola. And if it's positive, you've got a hyperbola. Just like that. No messy rotation, no crazy algebra, instant identification. Okay, let's bring this all the way back to the beginning. Remember our mystery equation? A was 1, B was -1, and C was 1. So let's plug it in. B squared is -1 squared, which is 1. 4 times A times C is 4 times 1 times 1, which is 4. So we have 1 minus 4, that's -3. And since that's less than 0, we know for a fact that our mystery shape was an ellipse all along. You know, finding a tool like the discriminant is just so satisfying. It takes what seems like a really complex, messy problem and just gives you this simple, elegant key to unlock it. It really makes you wonder, doesn't it? What other amazing shortcuts like this are hiding out there in plain sight, not just in math, but in everything we find complicated?